Good morning, everyone. So my name is Gaspare Varvaro, and I'm working as a researcher on the Institute of Structure of Matter of the National Research Council of Italy within the Nanostructure Magnetic Material Laboratory. So during this talk, I'm going to show you some results about our recent work on the fabrication of magnetoresistive systems with perpendicular magnetic anisotropy on flexible substrates. So flexible electronics has attracted growing scientific and technological interest in the last decades as it enables new product paradigms that are not possible with conventional rigid substrates. So flexible devices are indeed bendable, shapeable, elastic, lightweight, unbreakable, and generally require lower processing costs with respect to their rigid substrate counterparts. So nowadays, a large number of flexible electronics elements with various functions have been developed, so they can be used as single functional components or to build more complex integrated platform for different applications. So they include, for example, electronic skins, functional implants, soft robotics, and smart textiles, just to name it a few. So despite the manifold functionalities that are nowadays available for flexible electronic systems, magnetic functionalities have been added to the family of flexible very recently. So in particular, the efforts have been devoted to development of flexible magnetoelectronic sensors which differ for the sensitivity, the magnetic field range, and of course the operating temperature. So as concerned the GMR and magnetic tunneling junction devices that are the focus of this talk, so the focus has been on devices with in-plane magnetized layers. While before our work, no studies have been reported in the literature about flexible magnetoresistive devices with perpendicular anisotropy, despite they are of a great relevance for non-volatile memories that could be integrated with other components to obtain a complex and multifunctional flexible platform, being also of interest for sensing applications is recently demonstrated, for example, in this paper. So, despite the high potential of perpendicular magnetized spintronic devices, the fabrication of such heterostructure on flexible substrate is quite complex because they require generally suitable substrates, smooth surfaces, and sometimes also high temperature. And these features are not compatible with polymeric flexible substrates that are amorphous and generally have rough surfaces and low melting temperatures. Okay, so to fill this gap, so we recently worked in strict collaboration with many groups from Italy and Germany to develop a strategy to obtain magnetoresistive exterior structures on flexible substrate with perpendicular magnetic anisotropy. So in particular, we have investigated two different strategies, that is the direct deposition on flexible substrate and the transfer and bonding approach. So the main advantages and disadvantages of these two strategies are collected in this table. Briefly, the direct deposition on polymer flexible tapes is a very simple and one-step process that allows achieving a large area coverage despite only low processing temperatures can be used due to the low melting point of the polymer tape. In the transfer and bonding approaches, the whole structure is fabricated by standard methods on a carrier substrate, then it is transferred on a flexible substrate. So this approach allows using crystalline substrates, high temperatures, and then the system can be also virtually transferred on any arbitrary substrate. On the other hand, these approaches are generally more complex and lead to smaller surface area coverage. Okay, so as concerned the material, we focused on GMR spin vase with perpendicular anisotropy based on the cobalt palladium multilayer system, which present quite high perpendicular magnetic anisotropy originating interface between cobalt and palladium. So the GMR spin valve consists of a synthetic antiferromagnetic reference layer made of two cobalt palladium multi-layers separated by a ruthenium spacer and a fill layer consisting of a cobalt palladium multi-layers. The free and the reference layers are separated by a copper spacer with a thickness of 2 and 3 nanometers. So we chosen this system for two main reasons. So first of all, this kind of system is well known and can be used for many applications. Moreover, so it consists of several interfaces whose quality strongly affect the final properties of the system. For example, it can influence the magnetic anisotropy of the cobalt palladium multilayers. Also, the interlayer exchange coupling, the synthetic antiferromagnetism depends on the quality of interface. And finally, the quality of interface also affects the GMR ratio of the whole system. Okay, so here is a sketch of the heterostructure that was first sputtered deposited at room temperature on a thermally oxidized silicon 100 substrate as reference systems. So the magnetic measurements indicate the samples present the characteristic three-step behavior of perpendicular magnetized GMR spin valves with a synthetic antiferromagnetic reference layer, while the magnetoresistive measurements show a GMR ratio of around 4.5% in both the samples, in line with the results reported in the literature for similar systems. So the heterostructure was then deposited under the same experimental condition on a polyethylene and naphthalene tape coated with a flattening coating layer with a law reducing the surface roughness down to 0.7 nanometers. So using this strategy, we were able to obtain high quality heterostructures on a large here flexible substrate showing a high flexibility. Magnetic and magnetoresistive measurements indicate the main features are basically retained, thus suggesting that such flexible tapes can be successfully used to obtain even complex multi-layer heterostructures, provided that high fabrication temperatures are not required. So as concerned the transfer and bonding approach, we recently developed an efficient and a versatile strategy based on the low adhesion of a gold underlayer to a silicon oxide substrate. So the same multi-stack were first deposited under the same experimental condition on a 10 nanometer thick gold buffer layer grown on a silicon oxide silicon 100 substrate. Then, owing to the low adhesion of gold and silicon oxide, centimeter scale spin valve stacks were easily peeled off and transferred from the rigid substrate to a flexible tape by using a commercial adhesive polyester tape. So the magnetic and magnetoresistive measurements show the properties are basically retained for a copper thickness of 3 nanometers, while for a lower spacer thickness an inverted magnetic loop is observed, indicating that the topmost layer of the synthetic antiferro magnetic reference selected and the free layer are exchange coupled. So this effect, as well as the moderate reduction of the GMR ratio and the increase of the switching field of the individual layer, is likely due to the slightly higher roughness of the gold underlayer with respect to the silicon oxide, which can affect the final properties of the system that are strongly dependent on the interface quality. Okay, so it is worth noting that after the peeling, no significant changes are observed on the magnetic and magnetoresistive properties, thus suggesting that such a method that we developed can be pursued to obtain complex spintronic films in a large area flexible substrate, including systems of fabrication processes requires high temperature treatments. Okay, now to demonstrate that such a flexible systems can be adapted on a carved substrate, we perform a series of tests under bending conditions. Indeed, when a folded GMR spin valve with a perpendicular anisotropy is placed within a uniform magnetic field, so each region of the spin valve will experience a different angle between the applied field and the easy axis, and which can of course affect to some extent the magnetic and magnetoresistive properties. So to investigate the geometrical effects on the magnetoresistive properties, so the flexible system was placed on top of a semi-cylindrical support, and the magnetoresistive measurements have been performed as a function of the bending angle theta defined by this equation. So as shown in the slide, the shape of the magnetoresistance curves and also the absolute value of the maximum GMR ratio are not strongly affected while increasing the bending angle, and indeed we observe a very slight reduction of the GMR ratio even at a bending angle of 180 degrees. So to explain the observed behavior, magnetic and magnetoresistive measurements have been performed on planar samples by applying the external magnetic field at different angle phi with respect to the normal to the first surface. So as reported in these graphs, either the shape of the curves and also the GMR ratio remain almost unchanged for up to angles of 45 degrees. Significant changes are only observed at phi angles larger than 60 degrees. So this data these results have been then used to explain the experimental evolution of the GMR ratio open bending, which can be successfully modeled as the integral of the experimental angular trend of the GMR ratio of planar samples. So the very good agreement between the experimental data and the fitting curve demonstrate that the moderate changes of the GMR ratio is actually a geometrical effect. So in conclusion, for the first time, perpendicular magnetized GMR spin valves with a sizable GMR ratio were obtained on large area flexible substrate by using an innovative transfer bonding approach, exploiting the low adhesion of gold on silicon oxide and also the direct deposition of flexible polyethylene naphthalene tapes. So we also performed for the first time a bending test that demonstrated GMR ratio is always light affected even under a bending angle of 180 degrees, thus paving the way for the development of novel devices based on flexible magnetoresistive structures with perpendicular magnetic anisotropy. So before concluding, I would like to show you that we recently developed in collaboration with the group of Denis Makarov from the Helmholtz-Zentrum Dresden Rosendorf Institute, that this kind of GMR spin valve with a perpendicular magnetic anisotropy can be used to fabricate flexible magnetoreceptors for on-skin touchless human-machine interfaces. So, thank you very much for your attention.